Last year I spoke about Python, doing recommendations in Python, and especially hybrid recommendations, where you not only use collaborative filtering signals, but also metadata information. That was sort of my talk last year, and I guess every other talk at this conference and sort of other conferences this year and next year and probably last year as well is sort of on neural networks and deep learning. So I thought, oh, I'll capitalize on this and say how to do recommendations using deep learning. So here it goes. And throughout the talk, if you have any questions, just let me know. I'm happy to answer them. Okay, motivation. So the rise of deep learning has given us new and wonderful techniques and new and wonderful toolkits to do very fun stuff, and it's been incredibly successful in image recognition, it's been incredibly successful in machine translation, there are some amazing results in reinforcement learning, but what really is the use of recommendations? Like, probably the best recommender system you can deploy straight away in your application is just recommend the most popular item to everyone, and it'll do amazingly well, and like get you 60% of the way. And the other sort of workhorse of the recommender systems literature are the matrix factorization models, which are extremely simple and, again, work very well. So really, what's the draw of deep learning? What's the draw of neural network toolkits for doing recommendations? So my position on this is as follows. There are a bunch of huge advantages. Firstly, if you're using a neural network toolkit, you get speed of iteration. You can make changes to your model very, very quickly, try them out very quickly. You don't have to implement sophisticated SGD models by hand. You just change your loss function or you change your representation, and the neural network toolkit that you're using, it takes care of the backpropagation for you. So that's really useful. Another advantage is flexibility. So if you're using existing packages for recommendations, like let's say Spark, mostly it's a fairly fixed functional form, and there are only certain things that you can do. So in most applications, this will be collaborative filtering. You just have information on what users did and what items they interacted with, and that's what you put into your model, and that's what comes out. With neural network toolkits and with deep learning, you can do much more fun stuff quite quickly. So let's say for your application, the metadata of the items or the metadata of the users is very important. You can put that in straight away. And the final advantage is powerful representation techniques. So let's say in your application, the visual side of things is very important. So let's say if you're Etsy, a large part of how people interact with your items is what they look like. So something that you might want to do is put features of items which are visual into your model. So you take your classic factorization model or collaborative filtering model, and then you train a CNN on your images and you put that in, and hopefully that will make better recommendations. And this is something, again, that deep learning gives you and neural network toolkits give you. So in recommendations, these are the things that you can do. You can add side information. Again, images. There's a paper by Etsy where they look, oh, can we take the images of our products? Can we run a CNN on them? Can we take those representations and put them into our recommender system? Can we make better recommendations? Second advantage is flexible loss functions. So mostly what people do with recommendations is, well, if a user interacted with an item, that's a 1. If they didn't, that's a 0. That's a classification problem. That's what you do. Maybe that's not the best approach. Maybe that's not the best approach in general. Maybe that's not the best approach for a particular use case. Maybe you have both interactions, like the Netflix case or the movie lens case. You have both interactions. Did they watch the movie? But also you have ratings. Like, after watching the movie, did they like it or did they think it sucked? So maybe you want a more flexible loss function to take advantage of that additional information. And finally, sequence-based representations. So arguably for a lot of recommendation cases, you have a user that performs a sequence of actions on your website or in your product, and you want to take advantage of that sequence information to predict what they're going to do next, right? This is what's interesting. They bought these items in the past. What's the next thing that's going to buy? And, they may have bought books in the past, but if they just bought a camera, maybe batteries is what they want, or maybe a memory card. Okay, so the plan for this talk is sort of straightforward. The first is, how do you take a classic matrix factorization model and express it in a neural network toolkit? Once you've done that, well, the promise is fast iteration. How do you experiment with a number of ranking losses? And finally, well, if sequence prediction is what you want, how do you switch out the factorization representation for a sequence-based one? So instead of just taking users, the whole representation of everything that they've done in the past, maybe you want to take the sequence of most recent events into account more prominently. So as I go through this is going to be a fairly, my talk is going to have a fairly practical bent. I'm going to show implementations. So that sort of limits the complexity, but also hopefully will help to explain. And all the examples are available on GitHub, and let me know if you have questions, happy to explain. And everything will be done in PyTorch, which is probably what people don't have that much experience with, but I found it to be extremely expressive and quite pleasant to use. Okay, so I'm going to start with a classic model, the factorization model. Who here knows what a factorization model is for recommendations? Perfect, quite a lot of people, but I'm going to explain anyway. So in recommendations in collaborative filtering, what you do is you take information on what people interact with. So you have a set of users and a set of items, and you express it in this big sparse matrix where you've got users as rows and items as columns. And then if a user interacted with an item, that's a 1 in your matrix, and if they didn't, that's a 0. So that's quite big and that's quite sparse, and really what you want to do is factorize this matrix into latent representations of users and latent representations of items. So these are two other dense matrices that when you take their product, they will hopefully reproduce the original matrix that you have accurately, plus through discovering the latent structure of the problem, show you the items that given user has not interacted with yet, but would be interested to see. So this model was famously introduced during the Netflix prize contest and is still a workhorse in a huge amount of applications. And originally it was sort of in the form of ratings. People had ratings in the matrix and you wanted to predict rating for an unseen movie. But the more modern form of it is, well, actually the more important piece of information there is what people watched in the first place. So the implicit format of that problem is something that's used more often now. So a way of expressing this in neural network form is, well, you just take two embedding layers, an embedding for users, an embedding for items, and then you take when you have a user and you have an item pair, you take the user embedding from the user embedding layer, and you take the item embedding from the item embedding layer, take the dot product, pass it, let's say, through a sigmoid function, that's your prediction. So again, two embedding layers for users and items, connected by a dot product, and in this case, fit with logistic loss. So from that matrix that you have, you take your ones and you take your zeros, and you index your embedding matrices by those indices, take the dot product, and that's your score. So in PyTorch, you might do something like this. So the way you define a network in PyTorch is you define this class, which inherits from NN module, and then you define the layers that are in your model, and after that's finished, you then put it through an optimizer and do backpropagation. So in this case, we just define the embedding dimension, which is the latent dimensions of the vectors that you use. Then you define two embedding layers. In this case, the scaled embeddings. You want to make sure that as you start, the initialization has the right scale. And then maybe you want to have some biases as well. So if an item is very popular, then the bias will be high. If a user watches a lot of movies, they will have a high bias to sort of soak up the effect of a heavy user. So once you've done that, you define the forward pass. So given those layers, what actually happens in your network? So in this case, you take you can express your matrix as basically pairs of items. So if user 1 watched movie 1, that's a pair 1, 1, and that's what you pass into your neural network. So in this case, let's say this is user ID says 1 and item ID says 1, although this is of course a mini batch. You index your embeddings by those IDs, and then you transform them so you can actually do the multiplication. You do the multiplication, you add the biases, and that's the output of the network. So that's effectively your prediction. You can pass it through some sort of nonlinearity, like a sigmoid, but that's your prediction. So how do you, once you have the network, how do you actually fit it? Well, commonly what you do in these sort of problems is you have an output vector. In this case, the output vector would have, for a given user, would have a dimensionality, let's say, of all the items that are in your corpus with ones where they interacted with an item and zeros everywhere else. Now, for recommender systems, this is not an amazing approach. The reason for this is these problems are very high dimensional. So even in simple cases, you will have tens of thousands of items. In bigger systems like Pinterest or Etsy, you'll have millions of items. So you can't really have this loss function where on every evaluation you evaluate millions of dot products and then try to compute a loss from this. So what people do in recommendations instead is they use a sampling approach. So you take your positive pair of user and item, and then you sample randomly a negative item from all the other items, with the implicit assumption being, well, this user didn't interact with this item, therefore they're less likely to like it, so we should treat it as a negative. So that's a sampled loss function. And we can express it in PyTorch like this. The other display is too far away, I'm just going to walk to this one. So you have your users. So these are basically IDs of the users who have positive interactions in your data set. Then you have the items, which are the IDs of the things that they interacted with. And then you sample negatives. So in this case, I'm just going to say, well, for every user that I have in my mini batch, I'm just going to sample a random item that I haven't looked at. And that's going to be my negative. So then the objective of the network is to predict 1 for all the things that they interacted with, but 0 for the things that it didn't. So I have this composite loss where I want to predict 1 on the positives and 0 on the negatives. And in Torch, compute the losses, concatenate this into one vector. This is for a mini batch, so I take a mean, and then I can backpropagate on this. So we can actually run it. And again, all the code is in GitHub. So I'm going to use the movie lens 100K dataset, which is a very famous research dataset, but I guess at this point is sort of a unit test for your recommender system. So if your recommender system doesn't work on the movie lens 100K dataset, you have a problem and you should fix it. The nice thing about it is well known, it's easy to get, and it runs very quickly because it's just so small. So in this case, we're going to define a model, and we use the pointwise loss that I just described. Oh yes, I should probably say what the actual dataset is. It's a dataset of 100,000 interactions between users and movies, and basically you have a 1 in this case if a user watched a movie and a 0 if they didn't. So we want to fit a model, train a model, get the embeddings, and then at the end, when we evaluate it, we're going to construct a ranked list of movies for every item. And hopefully the movies that they have actually seen in the test set will be at the top of the rank list. And we're going to measure this with a metric called the mean reciprocal rank, which is very simple. Basically, for every ranking that you construct, you take the rank of the true positive items and take 1 over that. So if you rank the true positive item as 1, it will be 1 over 1, so that's 1. If you rank the true positive item as the 100th, it will be 1 over 100. So the closer to 1, the better. If it's small, that's a bad model. Yes, so let's run the model that we just defined. We have the pointwise loss, we put the data through it, we fit, and we produce the score, which in this case is 0.06, which is okay. But now that we have this neural network toolkit model, can we actually do better, and how easily can we do it? So one way of doing better is to use ranking losses instead of classification losses. So what we just run is a classification loss. So we have the representations with the embeddings, and then we have a classification loss, predict a 1 on the positive items and a 0 on the negatives. Now, a ranking loss is slightly different. What a ranking loss does is it says we don't actually care that we predict a 1 on the positives and a 0 on the negatives. All we care about is that we predict the positives, the score that we predict for positives should be higher than the score that we predict for negatives. And the way you do it is you construct triplets of a user, a positive and a negative item, and then say that the positive item should always be ranked higher than the negative item. So one way of doing this is this loss right here, which is 1 minus a sigmoid of the difference between the positive predicted score and the negative predicted score. So the higher your positive predicted score is, the smaller the loss. The higher your negative predicted score is, the larger the loss. So minimizing the loss ensures that you never flip the ranking between the positives and the negatives in your data set. So how do we do it with the model? Well, we use a Siamese network. So we use the same embedding representation from before. We compute the score for the positive and negative item using the shared embedding layers, and we feed it into the pairwise loss. So graphically, you can think of this as sort of like this. You have your representation model for the non-positive, and you have the representation model for the sampled negative. And you take your IDs, you pass them through the embedding layers, you get the embeddings out, you take the dot products, and then pass it into the loss. It's called a Siamese network because even though you sort of have two branches of the model, and in principle you could have different parameters here and here, in this case the parameters are shared. So the actual number of parameters in the model is exactly the same as we had before. And by the way, these sort of networks are often used for metric learning and that sort of stuff. So what might the implementation look like? Again, very similar to the previous implementation. You sample some negatives, but instead of just concatenating the two loss vectors, you feed it into the BPR loss, or the loss with the one minus sigmoid of the difference between the positive and the negative score. So do we actually get a better result when you run it? We do. We run the model with the BPR loss, and we get a slightly higher MRR of 0.08 instead of 0.06. So that sort of illustrates how nice and easy it is to experiment with different losses. Ordinarily, if you had to do this yourself, before the advent of neural network toolkits, you just have to code up the losses yourself and make sure that the SGD flows nicely and so on and so forth. Whereas here, you just define a different function, and the toolkit takes care of the rest. But given that this ranking loss works better, can we do even better? Well, we can, and it's called an adaptive ranking loss. So what we do is we have the positives, and we sample a set of negatives, but then we sample a couple more negatives for every positive, and then we pick the one that's closest to violating the ranking. Because remember, we have a positive and we have a negative, and we want to make sure the positive is ranked higher than the negative. But if we just sample the negatives randomly from the entire data set, we may find something that's actually not very discriminative. So if we sample as a negative a movie which is just terrible, that's not going to help us model tear apart what the user likes and what the user doesn't like. So what we can do instead is sample a couple of negatives, and then for the gradient step, pick the one that's closest to violating the ranking that we want to induce. That gives the model a better information about what the user likes. That's an excellent question. That's possible. That's possible. So what you probably wouldn't do is do exhaustive sampling. If you don't do it, you get the result that we just had. If you sample everything and then pick the highest ranked one that is not known to be positive, that is going to give you a terrible model, because you're going to be just defeating yourself as you fit the model. But if you do it, it's a hyperparameter. If you do it just the right amount, it gives you a better result.
But your factorization also takes into account that the negative should be negative. So the whole goal of recommendation is to find those negatives that are most likely positive.
That's true. Yes, there is a tension when it comes to this.
I also don't know a solution, but it's something that if you exacerbate that assumption, the negative factor that assumption.
Sure. And I mean, that's definitely a problem, and a lot of people have thought about this. I don't know that there's a good solution for this yet, but it's definitely a thing. There's a extension to this is if you show people items and then say, well, we showed this item to you and you didn't like it, we'll take that as a negative. So then you know that they have seen it, but you take it as a negative in the fitting of your model. That's not necessarily the best approach, because you may be interested in you may still be interested in the item, you just didn't have the attention span maybe to interact with it. And then if we take it as negative, we're just going to be giving you worse recommendations later on. But yes, that's a good question. So in fact, if we look at the implementation, this is very simple, and this is why PyTorch is so nice. When we sample the negatives, you just do a loop and sample a couple of negatives and compute the scores for all of them, and then pick those ones which have the highest predicted score. But I have a hyperparameter here which is hard-coded, which is a little 5. So we just sample 5 negatives for every user and pick the one that has the highest predicted score. But coming back to your question is, if we make this higher, the performance of the model actually falls. So I think this would be an example of where you have a self-defeating model. Yes. So again, this is a slight variation of the previous loss. You just sample some negatives, pick the one that's got the highest predicted score. So does this help? Yes, it does help if you pick your hyperparameters right. So in this case, we've got an MRR of 0.11 instead of 0.08 as we had before, or 0.06. So the ranking losses, they really do help. So a summary is you have the same representation, but you can very quickly iterate on the different ranking losses. And I just looked at ranking losses, but maybe you want to include the rating in your loss as well. And then that's super simple again, and then you can see if that improves your model. All of this is incredibly simple to implement, and you can easily write a loss function that suits your unique model. And that's something that used to be very hard. Now that deep learning has come into its own, it's like a windfall profit to us who don't maybe need extremely deep representation models. So the second thing I wanted to talk about is not here, but in the next example I will mention this. Yeah, that's a good question. So the second thing I wanted to talk about is recommendations as sequence prediction. So again, maybe that's the right way of thinking about this. We have a user and all we know about them is what they've done in the past. This is how we represent them. And maybe we want to encode this sequential representation in a model and treat the recommendation problem as a problem of predicting the next element in the sequence of user actions. So there is a number of ways of doing so, but they all consist in representing the user as a function of the items they've bought in the past. So the user representation can be a pooling representation. So we can just take the user as an average, or maybe the sum of all the representations of the items that they interacted with in the past. We can use a recurrent neural network, where we actually try to capture the sequence structure. So they did something a long time ago, and they did something else, and did something else, and what are they going to do now? And maybe you want to use a CNN. Maybe we think the sequence structure isn't that important, but maybe if we slide a CNN window over what they did, maybe there are some things that occur together that carry more information than just individual events. Yes, so the advantages, it captures sequential information. There may be less pressing need to retrain. Like in the model, in the representation model that I described before, every time you get a new action from a user, you need to go back to the training of your model and add that action into it and take a gradient step and update the parameters. In this case, the input to your model is just a sequence of events. So you can just train a model, and then every time a user carries out another action, you just expand the input vector into that model. You don't have to do retraining. Disadvantages, well, if you have a complicated model, it may be slower to evaluate. If your application is performance sensitive, that may not be feasible. Another thing is, well, is it actually worth paying the cost? If your data has no clear sequential structure, then there's really no use of doing so. And I guess that's why we're using the movie lens dataset. We'll see if so the sequential structure there is important. And again, here we're changing the user representation. All the loss functions that I talked about before, you can take them as they were and apply them to this model in the same way. So you can the choice, because of the flexibility of the formalization is so great, you can choose your representation dependently on what your loss function is. Examples. So to prepare your data for this sort of model, you need to construct sequences. So one way of doing this is your input matrix could look something like this. So if you have events A, B, C, D, you want to predict from 0 ABC to ABCD, where from 0 you predict A, and from B you predict, from 0A you predict B, and 0AB you predict C, where 0 is the null token in your prediction. And this is actually what I'm going to do here, because if we run a recurrent neural network over this, we can get the outputs of the network at every time step, and then use the output of that network as the user representation and use that for predicting the next item. That's actually quite nice. One alternative way of doing this is, which I think is more common because it's more flexible, but it has worse performance, is to split your sequences. So if you have a 4-element sequence, you split it into 4 rows, and in the first row you predict from completely empty sequence, you predict the first element, and then you left pad and you have the first element predict the second, and so on and so forth. This is more flexible, but then if you're using a recurrent neural network, for every of these rows, you run your recurrent neural network from left to right, and then you're sort of computing the same hidden states over and over again for this. So it's not quite as, it's not as performant. Okay, so given this prelude, I'm going to try a couple of representations. So I'm going to try the popularity representation, or the lack of a representation, a pooling one, which just averages a user's previous interactions, and a recurrent one, and see how it fares on the movie lens dataset. So the pooling representation, again, part of it is very similar to what we did before. We have the embeddings layer, but note that we don't have an embedding layer for the user anymore, because the user representation is, in this case, just an average or the sum of the representations of all the items they interacted with in the past. So we don't have that anymore. We only have the items. And then the forward pass is, well, you have some item IDs and item sequences, where this is what the user has interacted with in the past, and this is what you're trying to predict. You get the embeddings, and then you create a rolling sum, in this case, across the sequence. So the first element of your sequence will just, well, the first element that you did, and then the second one will be the sum of the 2 preceding ones, and so on and so forth. And that will be at every time step the representation for your user. And then you take the item biases and you do the dot product. So at every step you take, again, like before, a dot product between the representation of the user and the representation of the item. And then take the sum, and that's the dot product. And that's your prediction. The recurrent representation was very similar. Again, you have the embeddings, you have the biases, but this time you also have the LSTM layer. This is based on a paper that uses GRUs, but I'm going to use an LSTM here. So we have the item embeddings, item biases, an LSTM, and then in the forward pass, you take the embeddings of the items that a user has interacted with in the past and simply run an LSTM over them. And then at every time step, the representation of the user is the output of the LSTM at that time step. And to get the prediction, you take a dot product of that with the representation of the item that you're trying to predict, and that's your output. Okay, so let's try this on the movie lens dataset. We import the data in a slightly different format this time, so that we get the sequences. So this is what training rows look like. So from this sequence, you're trying to predict this sequence. You'll note that it's just shifted by 1. And we'll start with the popularity baseline to know that we're actually doing anything. So the evaluation here is, again, MRR, where at every step we want to predict the next item in the sequence. So with the popularity baseline, we get 0.12. If we move on to pooling, we get 0.14 on the test set. And if we move to LSTMs, which is the best and the most sophisticated representation here, we get 0.11, which is worse than the popularity one. So there are a couple of possibilities here. Did we set bad hyperparameters? Maybe the sequence information is not important. Or maybe, which is probably most likely, I got the model architecture wrong and it's doing something completely different than I thought it would be doing. So to get at this and try to disambiguate between those, we can run a very simple experiment where we just have something with very clear sequence structure and just use number sequences. So we use numbers as the IDs of the items, and then 1 always follows 0 and 2 always follows 1, and so on and so forth, and run the model on this. So if we do this and we use the popularity baseline, it has a terrible performance of 0.07. If we use pooling, it's slightly better. But if we use LSTMs, they perform really, really well. So at least the model is fine, which is reassuring. And it sort of goes back to the point that well, LSTMs are great if your problem has a sequential structure. But if it doesn't, maybe it's just overhead. Maybe it's just cost you don't want to pay. Okay, so in summary, what deep learning has given recommender systems is amazing flexibility. Like if you want to set your model up differently, you can. If you want to use a different loss, you can. If you want to add pieces of side information, it's extremely easy. The toolkit will take care of everything for you. Secondly, you have powerful building blocks. If you want to use images, well, you can use convolutional representations. Maybe you have enough data to be able to fit representations of your own. Maybe you can just use a pre-trained CNN and fit this into your model and it will work better. And the final thing is speed of iteration. Whereas previously you had to do it all by hand, now it's really, really easy and really straightforward. And you can think in terms of your normal NumPy operations and mathematics, and your model will be fit for you. Is everything perfect? No. Recommender systems are inherently very sparse problems. You have lots of users and you have lots of items, and neural network toolkits and neural network approaches work best with highly dense problems. Your CNNs are highly dense problems. And recommender systems implemented in neural network toolkits can be quite slow. The reason for this is, well, if you have this enormous embedding matrix for your items, which is maybe 10 million long and 128 floats wide, and if you update that entire matrix on every time step, on every gradient update when you're fitting your model, that's a lot of overhead. That's going to take a long time, and a lot more time than if you implemented the same thing by hand and used the sparsity of the problem to your advantage. So there are a couple of solutions to this. I mean, you can, in certain frameworks, you can use sparse gradients. So when you're updating the embedding of a single item, you don't have to update all the parameters of your embedding layer. You just update that one item. But that can still be quite slow. One alternative is, well, maybe you can run it on GPU with huge mini batches. So in other problems, maybe your mini batches are 64 or 128 large. In this case, well, maybe you want to run a mini batch of 8,000 examples at one time. Maybe that's the right way of treating sparsity, because your parameter updates are sparse, so maybe it doesn't matter if you run huge mini batches. And that actually works quite well. Yes, so I guess the takeaway point is they're very good. They're highly flexible. You can accomplish amazing things with them, but the performance may be a problem.